Welcome to day six of 30 days of machine learning. My name is Akshat Mishra, and basically, I made something of a pet project which consists of 30 different machine learning models, all the way from something as simple as logistic and linear regression, all the way up to difficult transformer models. Everything implemented from scratch. You can check out the models, and this is going to be like a short tutorial or like a video walkthrough for the specific models. You can check out the first five models. I have left the link in the description. This is day six of 30 days of machine learning. Today we have on our hands a breast cancer classification model using support vector machines. Very interesting problem statement. So without wasting time, let me start. First of all, we'll start with a typical pipeline that we have been implementing. So you can read the repo alongside or you can read it later. So this is the problem statement. It's very simple. We have a breast cancer data set, which is the sklearn inbuilt data set. Okay. Which means it is not external. So these inbuilt data sets, which are available within the sklearn library, they are very clean. They're very naive. There's hardly any missing values. There's hardly any issues with these inbuilt data sets. So the data pre-processing pipeline and all of the things we do before building the model in this case is very simple to do, which is why I've kind of skimmed through it so that we can get to the physics of the model, which is the interesting thing to discuss. So you can read the problem. Cancer treatment is always better when it is detected as early as possible. So a model needs to have a very good accuracy and to detect the correct values and have as many and have as less misclassifications as possible. Okay. So we have got two types of cancers, two types of tumors basically. One is the malignant tumor, the other is the benign tumor. Malignant means cancerous, benign means a mass which is not cancerous. So we need to classify between them, which one is which, based on some historical data. That is the problem that we are solving here. Okay. So the thing is, upon first look, you can basically say that why not use a naive-based classifier model for this, or something as simple as a logistic regression model. Because let me go to the board here. So if we look at this carefully, what are we solving here? If we look at this carefully, uh, we are solving a binary classification problem. Okay. Binary classification basically means 0 1 kind of classification, heads, tails, rain, not rain, yes, no, that kind of a problem. Here we are classifying benign or malignant. So that begs the question, why not something like a logistic regression, which we used in the first model in this repo? Or why not something like a naive Bayes? So there is a very good reason why we have chosen SVM for this specific problem statement. I am getting to that. So the thing is, this starts from the core intuition of SVM. For that, I'll have to take you guys to the data set. So this is the data set that we are using, the breast cancer Wisconsin data set. Okay. This is how to load the data set. This is basically the Python code. I'll be first explaining how we are implementing the model, and later we will, deep dive into the code. But the code part is very easy. It is just basic sklearn code, so you can look at it later. These are the dataset characteristics, 569 samples, 30 features. Now, this is the thing that I wanted to discuss. Okay, so if I go back to the board and show you, so we have got 30 features on our hands. It means that we have got 30 ways to define the masses. Okay, meaning that it's like tumor size, tumor radius, tumor shape, these kind of features. And as we know in machine learning, features and dimensions are interchangeable words. So we can also say that we have got a 30 dimensioned data set. Okay, like a data set having 30 dimensions. Now the thing that happens here is that in these high dimensional data sets, whenever we are tasked with classification, like we are in this case, we are given values of malignant, and we are given some some data points having their values as benign, and we are asked to, classify them. So, in these kinds of data sets where so many features are involved, it is always Very, very good. Very easy, in fact, to classify them if the number of features or the number of dimensions are many. What does that mean? So, in this case, we have got 30 dimensions. Now, that is a lot of dimensions. This is a very high dimensional data set. In such data sets, it is always easier to classify because there are many options to, classify the different target variables from. So this concept right here is called as the blessing of dimensionality. Okay, I repeat, this is called as the blessing of dimensionality. I have included this in the repo itself. You can read it later. This is right here. Okay. So the point of this is we have learned about the curse of dimensionality, where if the dimensionality of any data set is too much, it becomes very difficult to work with, difficult to visualize and really get an idea as to what is happening in the data set. But at the same time, dimensionality also brings us a positive use case. If it's a high dimensional data or a high dimensional feature space, it becomes easier for us to separate the data. Okay, because there are many possible ways to create a line to separate the data. This is called as the blessing of dimensionality. Okay, and this is specifically why SVM performs very well here. Okay. So this is the intuition here. This is how you can, go about your thought process to choose a model. Because like I said, a naive Bayes model and a logistic regression model would have just made as much sense as the SVM model has done here. But looking at the data, we were able to evaluate that due to the property of blessing of dimensionality, SVM is the more suitable model here. Okay. So continuing, so these are some of the features that we see in the data set. There are 30 such features, by the way. So it's a massive data set. Mean, texture, mean, perimeter. You can try it out yourself. This is the pipeline that we implemented. This is the same one we have implemented for all the days till now. It has not changed. Okay. Data set, EDA. Now, what have we done in the EDA? Let me show you in the code. First of all, these are the standard imports that we have done. Standard scalar, because this is a distance-based model, I'll just explain that in a minute. Cross validation score. I'll explain all of them separately, but currently let's just move forward. These are all the metrics that we'll be using to judge the model. And since this is an inbuilt data set, this is how we import such data sets. Okay. This is the EDA. I have commented it all out because there is nothing new in the EDA. Like I said, this is an inbuilt data set, so it's pretty boring to work with its EDA. There are no missing values. Everything is fine. If you want to look at the results, the EDA gave us a few interesting things to look at. So if I go back, this heat map was printed using the EDA. So, this basically, the darker the square, the higher the two features are correlated. So it gives us an idea as to how the target features are correlated to each other. This is called as a correlation heat plot or a heat map. It is available. It's a classic trick that we use in EDA, and it is used. No, it is implemented using the Seaborn library. Okay. This is to check for the missing values. There were no missing values. Df.describe gives us the statistical stuff. This is all old stuff. This is nothing new. Okay, you can look at the EDA. Using the shape, we got 31 features, which is actually 30 features. The 31st is the target variable, which means the benign or the malignant. Okay, so this is all pretty typical 80-20 testing split. Feature scaling, the first concept that we are going to discuss today, the first useful concept, by the way. So the thing is, whenever we talk about distance-based models, now by distance-based models I mean something like where calculations, mathematical calculations and distances are involved. Okay, logistic regression, linear regression, naive Bayes classifier, then SVM, all of these distances are involved. So whatever feature has the higher value dominates. What does that mean? See, let me show it to you. So we have got a total of 30 features on our hands. Okay. And of course, all features are not going to have the same values. Okay. Some features might be having a higher mean, some features might be having a lower value because there's radius in the features, there's perimeter, there's area, there's shape, all features are different, right? So in this case, what happens is that when we train the model using these raw features, the larger features, they dominate the model, which means they have a higher influence on the model output. Now that is okay, but what that leads to is a very, a very non-interpretable model, because the model is kind of ignoring the features with the lower values. We don't want that. We want the model to be more generalizable, which means it should take in account the values of all the features equally. Okay, it should be in a proper proportion. Okay, so that all the features have a similar contribution to the model to prevent the larger features to dominate. For that, we do something as standard scaling. This I have discussed before, but it's important, so I keep mentioning it. Standard scaling. It is available to use using the standard scaler in sklearn itself. It is another thing which is, uh, you know, inbuilt. So we use standard scaling. And what does standard scaling do basically? Let me change the color. So it basically, what it does is it transforms every feature to this value right here, x minus mu divided by sigma. Okay, anyone who has studied, the probability basics will know this. This is now old stuff. This is not new. Okay, so this is what it does, and x is the original variable. Mu is nothing but the mean of these variables. Sigma is the standard deviation, or the square root of variance. It's the same thing basically. Standard deviation. Okay. Now, what does this do? When we apply this to all of the features in our data set, it makes them very proportional. It brings them to a comparable scale. Because when we apply this, the mean of the entire data set comes out to be 0, and the standard deviation comes out to be 1. Basically, after we have applied the standard scaling operation, if we draw out the data set on a graph, it will look like the standard bell curve. Okay, it will look something like this. The most uniform bell curve to like ever exist. So it will look something like this. Okay, can make this here. Okay, this is 0. This is 1. This is minus 1. Okay, this is how it will look like. And this is very important. Why? Because we need to bring the features to a comparable range. So this is typical. This is the standard scaling. Okay, I'll show it to you. Uh, just a second. This is how we have done it in the code. Okay, we never fit on the test data because that leads to data leakage. So that's is again typical. Now we get on to the model. So, till now we have implemented the pipeline, done the stuff. Now begs the main question. What is the SVM model doing? What does it want? How is it working? Let's get into that. So for that, let me first give you the basic intuition as to, uh, just a second. Yeah. So I'll be first telling you as to what an SVM model does roughly, and then I'll deep dive into it to clarify it. Let me take this. Okay. So I'll be drawing a graph just to show you something. Let's imagine this is this line right here, and I draw another one. Wait a second. Yeah, and I draw another one. Uh, Yeah. Okay. So I've got this with me. Now, what I do is I just make this. So this is nothing. This is a typical graph that we use, like the coordinate plane. Now, what's happening in there is the more important thing to see. Okay. This is going to be loaded with tons of concepts and definitions. So just hear me out very carefully. This is going to be the best explanation of support vector machines, SVM, that you have heard till now. But just bear with me for 15 minutes. Okay. So, we have got two types of cancers to classify from. We have got malignant and we have got benign. So let's say the malignant are represented by this color right here. These dots. These represent the malignant cancer data points. Okay. They're all collected here. Okay. And then we have got the benign cancer data points. They look different because they are different, simple, of course. So they are distributed in here. They're different from each other, so they're all separate, which is why I've drawn them separately. Okay. So this is now, if you were walking down the street and I came up to you and I asked you, how will you separate these 2 points? It will be very easy. You say just take a line any line and draw a line between them, separating them. Something like this, right? This will be the answer that this line separates them. That is correct. That is correct. Yes, that is the answer actually. That is all that SVM is doing. This is the primary task and the intuition of SVM. SVM is, it is one of the most elegant geometric ideas in the entirety of machine learning. And I'll be explaining that why, but just hear that now. So this problem is almost tailor-made for SVM because this problem consists of a very high dimensionality data set that we are dealing with. Okay. So, now moving forward, what we want with SVM is that we want this blue line, okay? This blue line, and we want it to be as correct as possible, meaning that, it should not misclassify any point, and that, it should be accurate in doing the classifications between the benign and the malignant cancers. So this is the goal. Okay, let me first write it down. I will come back to the diagram in a second. There's lots of stuff to be done with the diagram. So if I write the goal of the SVM, what's the goal of the SVM? So the goal of the SVM model is to create a separating hyperplane between features. Okay. Remember this. This is part of the concept that we are going to be using. So this is the goal of the SVM model. Okay. Now, oh, wait a second. Uh, right, sure. Okay. So now, the second thing, there's going to be some terms that we're going to be using, and I'm defining those terms first so that you can really understand the definition as we move forward. So one of those terms is margin. Okay. So margin, you can imagine it like a page margin, like the one that separates the top and the bottom where you're not supposed to write. This is similar to it, but in the SVM, if we write it down, the margin is the perpendicular distance between the hyperplane and closest points on both sides, and closest points on both sides. Okay. So you can memorize these as well. These are actually typical definitions. You can find them anywhere, like in any evaluation or something. These are the ones which are asked, like what does a margin even mean? So back to the diagram. Let me first draw it again because it will be used again and again. We need a larger diagram to make things clearer. This was our diagram, right? And we have got few points here which are of the benign variety, the benign cancer data points. And then here we have got the malignant cancer data points. All right. So I'm just quickly drawing it again. Just, okay. Make this okay. And this was a hyperplane separating them right here. Okay. So now what is the margin? Now look at the definition. If we again read the definition, the margin is the perpendicular distance between the hyperplane. Now, first of all, the word hyperplane. What does the hyperplane mean? So this line that we just drew, this blue line right here, which is separating the two, this line is called as the hyperplane. Okay. Very easy, very simple. Why it is called as a hyperplane? See, because currently I am drawing it on paper. So it is like a two-dimensional thing. So to separate two dimensions, you need a line. To separate three dimensions, you need a plane. And what about four dimensions, five dimensions? It can be anything. which is why it is not called as a line or a plane. It is called as a hyperplane. It is like a universal word. So hyperplane can mean line, it can mean plane, it can mean whatever we require in the situation to separate the data points. Okay. So this is the hyperplane. Okay. And what about the margin? So again, going back to definition, perpendicular distance between the hyperplane and the closest points on both sides. Now we know what's the hyperplane. This blue line is the hyperplane, but what about the closest points on both sides? So let me show it to you. Can we simply say that these points, wait a second. Okay. Yeah. Yeah. So can we simply say that, these points, this one, the four that I'm circling, this one and this one are the closest points? Simple, they are the nearest ones to the hyperplane. So, let's just draw a dotted imaginary line passing through them in order to visualize this well. So I'll just draw this straight line right here. Okay. And I'll draw, another straight line right here. Okay. Now, if I go back to the definition again, perpendicular distance between the hyperplane and closest points on both sides, which means this distance right here, this distance. This distance is called as the margin. Okay. This is all very important. This will all be used in the calculation we are going to do in about 5 or 10 minutes. Okay. This is very important. This is all fundamental stuff. You need to be absolutely clear in here as to, what is the hyperplane and what is the margin. Because if it is all fit in here like a black box where you don't know what we are talking about, then there's no point of understanding this. Okay. So till now, very clear. These are our points. We have got the benign, the malignant ones in green, the hyperplane, and the margin, which is just the perpendicular distance between the closest points and the hyperplane. So now the definition is done. Now, one last thing, which should have been the first thing to be discussed, but it's fine. So, what is the full form of SVM? Support vector machines. So machines are machines, that's fine. What are support vectors? So very simple. These 4 points that we just drew, which are the closest points, closest to what? Closest to the hyperplane. These points are called as support vectors. Why are they called support vectors? I don't know. The guy who wanted to name them like that named them like that. Okay. This is again definitions. This is nothing to understand from. Just look at the diagram, understand it intuitively, keep memorizing. Support vectors. Now we go on to what the model is doing. So we have understood the basic terminologies used in the model, but now the main thing as to what the model wants. What does it need? Okay. What is it implementing? So, if we look at it in 3 words exactly, what does the SVM want? It wants nothing but the maximum margin for hyperplane. 5 marks are there. Okay? Wants nothing but the maximum margin hyperplane. So, we make that. Yeah. So, what does this mean? So as we saw that we have got the hyperplane here and in the margin. So the point of SVM is to increase this margin distance as much as possible. Okay. We want this distance, this margin distance to be as much as possible. Now you'll ask the question why? Why do we need to increase the margin? See, this is the entire strength of the SVM model. Whenever we are classifying points, we want the closest points to be as far as possible, because if they were correctly classified, they are going to be the opposites of each other. If they are classified and they come close to each other, it means the model is a very weak classifier. Because see this the green arrows, you look at the green crosses and the orange dots in here, they represent the benign and malignant data points. And if any of them were intersecting with each other, which means if the green one was in the orange or if the orange was in the green, then simply that point would be called as a misclassified point. We want as less misclassifications as possible. and we want the margin to be strict. Okay, we don't want to lose margin, which is why this margin distance need to be maximized. Okay, so maximum margin hyperplane means that draw a hyperplane between the features that we are separating and draw it in such a way that this margin distance get maximized. That is what we want to do here. Okay, so it comes down to optimization problem. It is a branch in mathematics where we either maximize value or minimize a value. So here, of course, as you can see, we are maximizing a value. Maximize whose value? Margin's value. Why are we doing that? Because that leads to a more accurate, a more interpretable, and a more strong SVM model. Okay. Now, now the physics of the model. The main thing. We are moving forward. This is good stuff right here. How to maximize this value? First of all, we'll have to calculate that value, right? See this margin, I've just written margin here, but what is the value of this distance right here? I don't know. I'll have to calculate that. So now let's get into the model physics. This is the most important part. Okay. I don't think anyone really explains this because this goes more towards the research side of machine learning, but it is the most interesting thing to learn at. I mean, I cannot use a model if I don't know how it's working in the background. You know, I don't recommend using it as well because if the model seems like a black box, then how can you be confident using it? Okay. So we need to maximize the margin distance. Now let me draw the graph again. So this was our graph. Simple. Okay. Imagine a weight vector. Okay. So as we know, machine learning models have weights and their features. So imagine a weight vector W, which is, drawn from the origin like this. Okay. And, this was our line, the dotted line that we drew for the support vectors on the benign side. And this is the maximum margin hyperplane. And this is the dotted line on the other side, which basically is representing you know, the line for the other side. Okay, let me draw this again. This is nothing but the weight vector. Okay. So now we are tasked with increasing this distance as much as possible, margin distance. So we need to calculate it, obviously. So how to do that? Going forward, when we look at this weight vector W bar, this is basically the weighted vector for all the features. So if we write it down properly, W is nothing but, W1 plus W2 plus W3 all the way up to Wn. Similarly, we have got the feature X. X is nothing but, X1, X2, and continued all the way up to X of n. So we calculate the weighted sum of these two values to get Wx plus b, which is how we represent all of the features. This is what we get. Okay, this is basically a representation of this W vector right here. Okay. Now comes the main thing to understand. Okay, very important. So, what I'm saying is that this is the equation of hyperplane. Okay. So the hyperplane that we drew right here, let me change the color quickly. This line that we do right here, this is the hyperplane as we know. So, if we want to find the equation of this line, it's going to be nothing but Wx plus b that we have found right here. This is the equation of the hyperplane, basic coordinate geometry. Okay. Now, very important, very important, very important. If I write it like this, Wx plus b is equals to 0. Okay. Now, if I do a mathematical operation and multiply both sides by 5, so let's just do that. W multiplied by 5x plus 5b is equals to 0 because 0 multiplied by 5 is 5. And let's say I also do a different operation where I multiplied by minus 1. W multiplied by minus 1 multiplied by x plus minus 1 multiplied by b is equals to 0. Okay. Now, compare these three equations very carefully. These three equations, look at them very carefully. What is happening here? The point that I am trying to make by doing these multiplications is that these three equations that I just did, this one, two, and three. These three equations are the same. Why are they the same? Because well, I've just multiplied this second one by 5 and I've just multiplied this third one by -1. How are these equations different? These equations are representing the same hyperplane that we are talking about. Now, this creates a problem for us because, moving forward, we need to, minimize this distance, this margin distance right here. And for this, we need to get a definite answer. But if we don't know the definite equation for this hyperplane, how can we move forward? We don't know a definite equation because this is also correct, this one is also correct, and this one is also correct. They're all proportionate to each other. So how do we move forward? How do we select a definite equation to represent this hyperplane? So we do that by using a concept called as canonical scaling. Okay, it is pretty simple. The word just sounds pretty big. So what we do in canonical scaling is that uh, how we discuss it, we are telling the model that, the equation is increasing its value arbitrarily. Okay. We can multiply the original equation, this equation by 100, by 5, -5, whatever, and we are getting the same value. So we are taking that rule away. What we are saying is that now the equation is not allowed to scale like that. So now we tell the equation that, this is what you are going to be doing. So we take a value y, which is nothing but the output value y of I. And what we do is we multiply it with the equation of the hyperplane. And we tell the model that this is the valid equation. Okay. So, whenever you calculate the hyperplane, you calculate this. Okay. And, if it is a benign model, you calculate something like, let's say, wx1 plus b. And if it is greater than 0, you say that, yeah, it is benign. And if you calculate some other point wx2 plus b and it comes out as negative, you say that, yeah, it is malignant. Because these two values are always going to be different, which is how we are going to do the classification. Because, this is the hyperplane equation. Here are all the points of the malignant and here are all the points of the benign. So since this equation is wx plus b is equals to 0, all the points lying above it are going to have a positive value for this. And all the points below this are going to have a negative value for this equation right here. Okay. And what we are saying is, we are saying that rather than arbitrarily increasing the value of this hyperplane, we want a definite value. What is that definite value? Nothing. You just combine the output with the original equation. Because, we have got yi here. See, you can look at yi. So yi is going to be nothing but either +1 or yi is going to be, -1. Okay. So this is a very neat trick. This is basically a basic scaling trick. So now we have a definite equation of the hyperplane and we move forward using this equation. Okay. So now if I go back to the diagram, I wanted the shortest, I wanted the longest margin possible, which means I wanted to maximize this distance. So for that, I need to calculate the distance between some point which is lying here and the hyperplane. I need to calculate this distance, right? So how do we do that? So again, what is the equation of the hyperplane? So let me write it down. This is the equation of the hyperplane that we just calculated. Okay, the original, just a second. Uh, yeah, the original equation. Okay, and let's imagine some point x naught. Now x naught, it can be anywhere. Let's say x naught is somewhere here. Let this point be x naught. It can be anywhere. I'm just assuming it for the sake of calculation. So we have this. Now, what I'm asking the model is that what is the distance between this point and this line? Okay. Again, I'll say this. What is the distance between this point and this line? To correctly put it forward, what is the perpendicular distance between this point and this line? Why the perpendicular distance? Because the perpendicular distance is the shortest distance. Okay. So if I try to show it to you, you know, Let's take a line right here. Okay, let's call it AB, and let's take a point P. Now I ask you that give me the shortest distance from P to AB. Now you can draw this distance, you can draw this distance, you can draw this, you can draw this, you can draw this. Out of all the distances that you can draw from P to AB, this distance, which is perpendicular, will be the shortest. This is a basic mathematical rule. That is the same thing that we are applying here. So to find the distance from Wx plus B to x naught, we need, let me write it down here. We need distance in the direction of the perpendicular from the hyperplane. Okay. So what does this mean? So we have got the hyperplane here. Let me quickly get back to the diagram. So this is the hyperplane. Yeah, right here. So, when we draw this weight vector W from the origin till the hyperplane, this right here is perpendicular. Okay, this is a fact now, because it is perpendicular to the hyperplane. Now, what we are saying is we want the shortest distance from this x naught to the hyperplane. So we can safely assume that if we are talking about the shortest distance, we want the distance to be perpendicular to it, because all of the shortest distance from the hyperplane are perpendicular to it, meaning that the distance from x naught, if we want it to be the shortest, it also needs to be perpendicular to the hyperplane, which means that this needs to be perpendicular. So we can say that basically this distance, let me do it again. What we are saying is that distance of x naught from hyperplane must be in the direction of the perpendicular. So we need to find the direction of the perpendicular in order to get the minimum distance from x naught to the hyperplane. How do we do that? See, we have got the weight vector W, which is perpendicular to the hyperplane. So we can say that the unit vector of W will be the one which is, representing the direction of the perpendicular. So how to get the unit vector of W? Very simple. To get the unit vector of W, we multiply, we divide it by its modulus value. So this is the unit vector in the direction of the perpendicular. And now if we need to get the minimum distance, we basically multiply this by x naught. So, when we project x naught onto it and get the final result, we get nothing but W into x naught plus B, and divided by the modulo. Okay. So this is the perpendicular distance from any random point x naught to the hyperplane. Okay, this is a very important result and it will be used in the next step forward. Okay, so moving forward, now, if I take the diagram again, uh, since we need this distance, the margin distance, can we say that to calculate the margin distance, if we calculate the distance between, let's say, a point x1 here and some point x2 here, can we say that this distance, if we try to maximize this distance, that will be our answer? Can we say that? Yes, that is exactly what we are going to try and do. So for that, we do nothing but we take the equation of both the lines. So we have got the two parallel lines from the hyperplane, the one below it and the one above it. So the equation of those two lines, we take them as, just a second, yeah. So we take them as nothing but Wx plus B is equals to 1, and Wx Wx plus b is less than uh, is equal to minus 1. Okay, simple equations, quick. So now let's imagine there is a point x1 on this line and there is a different point x2 on this line. So we plug in the values of x1 and x2 in these lines to get this wx1 plus b is equals to 1 and wx2 plus b is equals to minus 1. Okay. Now upon subtracting these two equations, we can get something like x1 minus x2 is equals to 2. Okay. This is a very important result and we keep that. This is equation number one. We are going to be using that in a second. Okay. So we get to this result. Now, this begs the question that this value of x1 minus x2, what does it mean? So if we check out the diagram once again and we look at the 2 points x1 and x2, so what is x1 minus x2? Can we safely say it is the vector distance between the two, it is the margin distance basically, or we can say the vector distance between the 2 points that we want to calculate? Because x1 is a point on this plane, x2 is a point on this plane. x1, x2 is basically the vector which is connecting those 2 points, and we want to calculate that distance. Okay. But there's a constraint. We don't know whether this distance x1 minus x2 will be a perpendicular distance. But whenever we calculate the distance between two planes, the only valid distance that is that the distance that counts is the perpendicular distance or the perpendicular component of the distance, which means that this x1 minus x2 should be perpendicular. Okay, it needs to be perpendicular, otherwise it will not be valid. Okay, it will be an invalid result. We want it to be a valid result. So how do we do that? So for that, we got the unit vector result before, where this was the direction of all the perpendicular distances. We use this, and what we say is that, okay, this is the direction of the perpendicular distances, and this is the one that we want to be perpendicular. So we project this equation 1 onto this basics of linear algebra. So upon doing that, we are gonna get something like x1 minus x2 multiplied by w divided by mod of w. Okay. And now it's just over because when we go back to this equation 1, we can see that w multiplied by x1 minus x2 is 2. So we plug in this value here to get nothing but 2 divided by modulus of w. Okay, final result. This is it. Okay, what is this? What is this thing that we just calculated? This is the margin distance. Okay, this is the distance that the model is maximizing. Okay, or tries to maximize this distance right here. This. Okay. But now we haven't really maximized it. So let's get on to that very quickly. So how to maximize this value? See, if you look at it in a naive manner, this value, just a second. So if you look at it, in a very simple way. So 2 divided by modulus of W. So the value of 2 is going to stay 2 because it is a number. So to maximize the value of this entire, calculation, we need to minimize the value of mod W. The less this is, the higher the value of this entire thing is going to be. So we need to decrease the value of mod W. So to decrease it, let's say we can write it as, we need to minimize mod of W. Can also say that, we also need to minimize mod of W square. It means the same thing. Why are we squaring it? For the sake of calculation, simply. Okay, we can also say that we are minimizing the value of half of mod W squared. Okay, simple, direct. So our optimization problem eventually boils down to this. We need to minimize this. So, we go on to minimize this. It is a very complicated derivation, which there is no point of me including that. It is using Lagrange multipliers. If you have studied the concept, you can use it, but this will go beyond and we don't need it. But after solving it, we basically get our result. And our optimization problem is to minimize half mod w square with respect to this constraint right here. Okay. This is what our optimization problem boils down to. Okay. This is the essence of the entire model. Whenever you just click to use the support vector machine or the support vector classifier regressor, both of them are available for use. This is what is happening internally. Okay. This is what is happening when you are running the model. Okay, so this is all for the model physics. Now, quickly, if I go on to explain the other stuff, there isn't much remaining. So, this is the entire model physics. You can read it. This is how you classify class 1, class 0. Okay. This is the mathematical intuition. See, this is the same results that is derived. The repo has a lot of amazing stuff to read from. You can read it and see maximizing the margin, which we talked about. That is the entire thing the model wants to do. It improves the model generalization. This is the blessing of dimensionality. We discussed this as the first thing. Now, getting back to the code, uh, after the feature scaling, we have got the model. So uh, yeah. So the thing is, in the SVM model, we have got different types of kernels involved, which means different types of functions that we can use to classify the model. There's the linear function, there's the quadratic, and there's the RBF. What's the difference between these three is that linear is the most naive. Linear means clean separation, where we have got two values and we simply separate the two values between them. RBF is more suited to real world data, where there are few points which are misclassified, few points which are not as accurate. So RBF is very good in these cases. You can look into the details of this, but I think we did the broader chunk of the entire math. Okay. And it is time to discuss these three very important hyperparameters. There can be more, but I've taken these three. I'll quickly discuss them. So, like I said, that when we are talking about the SVM model, we want the maximum margin hyperplane along with along with minimum misclassifications, meaning that it shouldn't happen that our model is saying that one of the cancers is benign but it is actually malignant, or the other way around. That is called as a misclassification. They're very costly in models. We don't want that. Okay. So the thing is, wherever these trade-off kind of demands are involved, we are maximizing one, minimizing the other. We cannot achieve both at the same time. We need to settle. We need to find a middle ground. In this case, the parameter called as C comes in. Okay. C is a very important parameter that basically controls, how many misclassifications are allowed. So if the value of C is small, then what happens is that large margins are allowed. This is all given in the repo as well, but this is important, so I'm just going through it quickly. Large margins are allowed, and since the margins are large, there's always going to be more room for misclassifications, because we are saying that okay, the model can be loose, the model can be as wide as possible, and it doesn't really care about whether it is misclassifying the data points or not. It might misclassify, it might not. We are giving it the freedom to do it. So this may lead to underfitting and the formation of a very simple and a very naive model. Okay. Conversely, if the C value is large, then the model will form very strict, very small margins. The decision boundary will be very sharp. There will be an overfitting risk because the model will be like, I cannot make any misclassifications. I need to be correct every time. For that, it will try and overfit the data, nearly memorize the data. So that too will not lead to a very pleasant situation, which is why what we have done here is we have taken three of the most popular values of C, and we have done great. We have used grid search CV. for the hyperparameter tuning. So what it will do is it will take all these three C values and the two kernel values and the two gamma values, and it will run all of them to run, 3 multiplied by 2 multiplied by 2, 12 experiments in total. And out of those 12, it will return the one which gives us the best accuracy values. So let's say that C equal to zero point 0.1 and the kernel RBF and gamma scale. These three gives us the best values, so it will go forward with that. That is the beauty of grid search CV. So it's all basic. Okay. Now coming to the kernel, like I said that you can use any of them, but the RBF is more suited in real world data, high dimensional data like the one that we have here. So RBF has given us a higher value in here. You can check out the results. Gamma. Gamma is another very important hyperparameter. Let me quickly draw it to show it to you. So gamma, this is what the gamma symbol looks like. Gamma, its property is very simple. It basically decides the influence of individual points. Okay. First, understand this quickly. Influence of individual points. Okay. So what's happening in here is that if the gamma value is going to be something small, let's say it's a very small gamma value. What's going to happen is that far points are going to have more influence. Far points are going to have more influence. There will be obviously an underfitting risk, and the decision boundary will be very simple. Okay, very easy to make. If the gamma values are large, conversely, the near points are going to have more influence. There will be an overfitting risk, and the decision boundaries will be very sharp. So by far and near points, I mean nothing but the points which are close and far to the hyperplane. So these points right here, these ones, these are all very far from the hyperplane. And points like this one, points which are the support vectors, which are lying on the planes, they are very close to the hyperplane. So they are going to have a higher influence if the gamma value is too large. Okay. Now, coming back to the code, you can see gamma has two values, scale and auto. So scale and auto is different. It is just a way in that, we use to calculate the gamma values. So there's two ways to calculate the gamma values. You can check it out if you want to. So, what happens is that gamma can be calculated like this. This is the formula which is running in the background when you calculate gamma. This is what happens when you take gamma equals to scale. And when you take gamma equals to auto, this happens. Now, what does this do? Very simple. The first formula is the advanced formula, which is the one which gave us better values in this case. This just looks very naive as well. What's happening is that this gamma right here, when we use the scale, it adjusts the value of gamma based on the features, which means the dataset dimensions and the spread, which is controlled by the variance. So it gives us a more interpretable model and basically higher accuracy. Auto is a very naive model. It is usually used for very, very small data sets. So it is pretty simple. It just is the inverse of the data set dimensions or the features. Okay. So this is it for the gamma one. Now moving forward, you can check out the code. It's pretty simple. This is how we get the best set of values out of the grid search CV. These are the scores, predicted and value scores. We also made a simple heat map to show the confusion matrix. You can check it out right here. ROC curve is printed. It gives us the ratio of the true positive rate and the false positive rate. And this is the comparison line. If the model is close to this line, your model is horrible because it means it is a random guesser, like a coin flip. The more it is towards the top left corner, the better ROC curve is there. Always remember that. Okay. This is what we have plotted in its entirety. An extra thing, we have done this probability is equal to 2 here. What this does is that, it runs something in the background which is called as Platt scaling. What Platt scaling does is that it converts the raw output values from the support vector classifier and converts them to probability values. Basically, when we run this model, we do not get probability values as the output. We rather get, support vector classifier math done in the background. And then in the output, we are rather getting, which data point should the current point belong to, either benign or malignant, which target variable should it belong. But if we want the correct probabilities, probability is equal to true is the keyword that we use. Okay. So this is it for the code. You can check it out. The repo has more stuff if you want to read from it. This we did a small visualization in order to see how the boundary between the two data points is made. So you can see this as well. This is the equation of the hyperplane. This is all old stuff. Let me move forward. You can read this as well. This is the same that I explained, how different values of C, gamma, and kernel control. Okay. So linear is the straight hyperplane that I drew for you guys. Polynomial means a curved decision boundary. RBF means a non-linear decision boundary. Okay. So RBF is more suited to real world because real world data is never linear. In this case, we had linear, so linear worked fine, but RBF still gave us a better value. Okay. This is the equation of the RBF. You can see this. This is the tuning, validation. These are the metrics that we used, ROC, AUC being the most important because accuracy gives us the overall correctness, but in a classification problem statement, accuracy is often very misleading. So we do that, ROC values, time complexity, you can check it out. Since we are calculating distances between different points, distance calculation takes approximately n square because of the coordinate geometry formula. And since it is being repeated for d dimensions or d features every time, it will be nothing but an n square into d. So this is like this is a con, okay, because it is a quadratic scaling time complexity. If this value of n is 50, the complexity will be 2500. If it is 100, it will be 10,000. So it is increasing. Now this is one of the major disadvantages of SVM that it is very poor with scaling. Okay. And the space complexity, basically, what does the SVM store? It stores the value of the support vectors. So whatever the support vectors are, S multiplied by the dimensions, which is 30. The 30 multiplied by the number of support vectors. Very small, insignificant space. These are some situations where you can use SVM. Again, like I said, when we scale to a higher data set, SVM fails because this time complexity explodes too much. So it is always better to just use SVM when the data set is small to medium. Upon higher or larger data sets, we will have to go towards a neural network based solution. Okay. And if the feature space is high dimensional, of course, we go for SVM because of the concept of blessing of dimensionality. And yeah, if a clear margin exists, then it is a tailor-made problem for SP. This is some situations, you can read all of this. This is simple. These are some of the engineering trade-offs. The interpretability is low because SVM is not always clear. Latency is okay because the calculation sometimes takes time. Training speed is slow for large data sets. These are some failure cases, cases where SVM usually fails. So we need to tune the hyperparameters correctly. Training is sensitive to data size. You can read it. This is all simple. This is a small experiment that I did. I have included this in the repo. I'm not discussing it separately. It basically proves what the theory told us that, as the dataset size is increasing in batches, 100, 200, the training time is also increasing. So this proves that whenever we use a high sized data set, uh, SVM is a poor choice. So you can see this. Uh, this is the kernel selection insight that linear will be faster. Of course, RBF is going to perform slower because the equations are more complicated, but RBF is more suited to real world patterns. Okay. Yeah, this is it for the entire model. You can read more stuff for it, by the way, but you won't get a more detailed explanation for it. This is the entire code. So, one very important thing. I imported PCA here, Principal Component Analysis. So where was it used? So PCA is used to reduce the dimensionality of any data set. Since we have 30 features here, and I wanted to, plot this or plot this, any of these. So to plot this, I cannot visualize 30 features. How can I visualize 30 dimensional data set? I cannot even visualize 3D clearly. And I wanted to visualize it. So how do I do it? I reduce it. I reduce it from 30 to 2 in order to create this graph. This is why the PCA is used. And this is typical code. This is all handwritten code, so it's typical. Okay. There's the decision boundary, SVM train, Fogs, the ROC curve. I'm just seeing if we didn't miss anything. No, I don't think so. Grid search CV has been done. ROC curve. Okay. So I think this will be it for the model. I have tried and discussed the math in as much detail as possible so that nothing seems like a black box, because there is no point of using a model if you don't know what is happening behind it. You can revise it again if you want to, and just it's very important to know about the trade-offs that we are dealing with in any model. So with that, it's a wrap. I will go on to the day 7 model tomorrow. Let's check it out what it is. So for day 7, we have a SMS spam classification using naive Bayes. Again, a 0-1 classification problem. Very interesting to work with. Thank you so much.